And thanks to the organisers for inviting me. It's a great privilege to be here, and it's been a great couple of days to hear some fascinating talks from such a diverse range of aspects. And my kind of aspect, I suppose, is the hydrology. So I'll just bring this up. And I'm going to be talking about some aspects of the hydrology which make it challenging to model and to, in modelling, to help manage these river systems. And I'm going to, it might sound like a litany of excuses why hydrologists can't do their job properly, but I hope it's kind of a plea for understanding about what are some of the particular challenges in these river systems and how we need to get more information to help us understand them and to be able to quantify what's happening in these systems. And they can go from, these are a couple of pictures from the Neils on the western side of Lake Eyre, but we can go from something which people on the eastern seaboard will recognise as a river, nice channel, floodplain, to something like this, which is roughly in the middle of the floodplain, very poorly channelized. And in the Cooper, you can go within a few kilometres to these different types of systems. Okay, so I'm going to talk about where, when, how much, aspects which help us quantify flow. So things like the where is the spatial variability, which is really characteristic of this system. And it goes from rainfall, which can be very patchy, which you all well know, patchy runoff, and then of course the spatial patterns of flow, which are really quite spectacularly variable and different. The when is we can have quite a range in our, both in the seasonal, so this year obviously been a late start to the season, so quite a range in variability within the season, but of course enormous variability between years, so you know, that's just really a typical characteristic of the system. And as a hydrologist, we want to know how much, and one of our basic building blocks of data is, of course, stream flow gauging, so discharge, or the volume of flow passing a point. And the Lake Eyre Basin is characterised by very few stream flow gauging stations, and even relatively few rainfall gauges as well. So even our major input, rainfall, which we use to generate runoff, is you know, it's got a, it often can't capture the variability and the patchiness of that rainfall. And so putting these all together, our capacity to determine how any developments might change the river system is really contingent on being able to model or try and predict how those changes will affect other parts of the river system. So that's why it's quite important to be able to come to grips with these limitations. So just a slide to illustrate the spectacular nature of the river systems. 2010, huge flood coming down the Cooper, already water in the lower Cooper, the Bulloos going, water coming down the Diamantina. So we can use kind of new generation information, so things like from satellite images to help us understand these river systems and to be able to use this information to improve our modelling. But even particularly in some of the smaller systems where the remote sensing can't quite pick up the flow patterns as well, there's still nothing beats having on-ground information. So onto that on-ground information, this picture here is from a paper by Mark Kennard from Griffith, and Mark and co-authors looked at over 800 gauging stations in Australia. My point in using the picture is to illustrate the difference between the Murray-Darling Basin here and the Lake Eyre Basin in terms of monitoring. So Mark and co found, or they used 100 or more than 160 gauging stations in the Murray-Darling Basin, and they were only using gauging stations on the more unregulated parts. So on the regulated parts of the river system, on the Murray and the Darling, there's far more than 160 gauging stations. In contrast, in the Lake Eyre Basin, they found 13 with records of about 15 years, and that's pretty much the sum total of gauging stations in the basin. So essentially that shows the difference in investment in infrastructure in terms of understand and manage somewhere like the Murray-Darling Basin compared to the Lake Eyre Basin. The system, it has improved in recent years. We've had some more investment, particularly from the Bureau of Meteorology, put in money to the states, and there's been several gauging stations reinstated in Queensland and some new ones put into South Australia. Now, the gauging stations are measuring, it's important to remember, they're measuring water level. To convert that to flow past a point, we actually need to measure that flow at different times, and then we construct a curve so we can relate our water level to the volume of water passing a point. And that means we have to actually go out there and do gaugings, and that's so part and parcel of the investment in the infrastructure you also need to have that investment in time and resources to get people out there to measure the flows. And I'm going to illustrate some of the aspects of this spatial variability, the where aspect, using a couple of examples. So one from the Lower Cooper and then one from the Windora Reach of the Channel Country. So the where is really quite challenging in terms of understanding and modelling these systems. So here we have the Cooper coming through the Queensland-South Australian border in a mink about here, and it splits, goes up the northwest branch towards the Coongie Lakes here, and then the main branch through here. So the Coongie Lakes, Ramsar listed wetland, you know, it's kind of one of our iconic sites, I suppose, more well-known sites in the Lake Eyre Basin. And so in terms of being able to predict how changes in the flow regime might affect somewhere like that, obviously we'd need to know what this split is. And that's something we actually don't know. We don't have any kind of long-term data on these kind of key points in the system. And just to illustrate that, last year I was able to measure flow in all the channels that had access to a boat. So roughly 50% was going up to the northwest branch and 50% was going into the main branch. However, the year before, when I didn't have a boat, I could only measure a couple of sites, but 34%, so roughly a third was going down the main branch, this part of the main branch, implying that it was quite a switch between the amount of water going down the main branch and the northwest branch. So that kind of basic information where we need to actually measure flows going over a range of flood sizes is really critical for being able to determine where the water's going, as simple as that. The Channel Country around Windora, you know, the type example of these huge anastomosing floodplain systems. Here we obviously have extremely wide floodplains, and there's various flow paths where water can go down through here. I mean, there's thousands of channels, etc., in there, but in terms of determining the amount of water as it passes through Windora through to Nappamerri, we need to understand where the water's going within this reach as well, which people on the ground probably have a very good understanding of that, but being able to translate that information into a mathematical model, that's the really challenging part. And so, just as an example, this is a graph showing, this is from work taken from some people from University of Wollongong, David Knighton and Gerard Nansen, and they looked at the Curra River record, and so each of these blue dots is a flow event. Some of them are kind of lumped together. So this is the volume of that flow as measured on a log scale at Curra River, and here is the fraction of flow which would go to Nappamerri. So 1 means that all the flow at Curra River would go down to Nappamerri. 0 means all of it would be kind of lost in this reach. So I'm using the term transmission loss. That's, you know, a hydrological term. It has no kind of value judgment about that water. Obviously that water is going to beneficial flooding and ecosystems within the reach. But the important thing to note is that huge amounts of water are retained in this reach. So on average it's about 22% gets through, 78% remains in the reach. And for many flood events it's up to 90 or so percent. Now other work done from University of Wollongong by a guy called Josh Larson, he looked at the chemical signature from water samples at Windora versus Nappamerri, and he found that there wasn't any strong evidence for a big evaporative concentration of salts in the water that you'd expect if you simply had a system which lost water through evaporation as it went from the top to the bottom. So what that implies is there's flow paths within this reach which probably are quite efficient at getting water from Curra River to Nappamerri. And conversely, there's flow paths there which are probably relatively inefficient in terms of conveying water, and so that water is lost to parts of the floodplain and then seeps into the ground or is evaporated away. So again, and so if you think in terms of, say, the Curra River or the Windora irrigation licences, it's important to know where any particular irrigation licence would be taking water from which particular flow path for us to predict what's going to happen at the lower end. And the question then is, so are these flow paths susceptible to change? And a few people have touched upon this. So I've got an example here from the Lower Cooper, but things like roads, bunds, levees, pipelines, etc. We all think that they probably can, or they may be able to affect change, but we really can't quantify that because we don't really have often have these patterns of flooding prior to any infrastructure being put in and then post. So the example here is flow comes into the main branch about every year, and then larger events are needed to get through the Embarker swamp area, which is a big flat lignum swamp, and then on into the channelized parts of the main branch. Now there's a number of oil and gas installations down here with bunds going out to them, and we don't know if there's any change in the flow patterns from those, but just using this to illustrate the point that areas like this are actually quite susceptible to change. So if you start detaining water in those areas, and you can change the frequency of flow coming out of the system from, say, a 1 in 2 year type frequency to maybe 1 in 3, and that's what we have to be quite wary of. And we need to have this information about not only kind of how much water is passing a point, but these spatial patterns of flow. And even when it flows, so the Cooper is reasonably well gauged in terms of the Lake Eyre Basin, the Diamantina slightly better, the Georgina. There's relatively large catchments and then sub-catchments within our large catchments, so Kyabra Creek, Wilson River, etc., where we don't have much information at all about how often they flow. So the Neils is one. This is 34,000 square kilometre catchment coming into Lake Eyre on the west side. It's quite significant in terms of size. And we've had some inexpensive water level loggers measuring the occurrence of flow events since 2000. So if you looked at this period here, what we found was from 2000 to 2009, so we had roughly slightly more than one flow event per year at the site. And then in the wet period, November 2009 through the end of 2011, in that just under two year period roughly, we had the same amount of events as we had in this previous period. So in terms of water resource management, just this basic information about how many flows, how often they flow, what's the duration of no flows, is quite difficult unless you've got a really long-term record. And this second graph here is from some modelling I've done in that catchment, and that's suggesting that this period here from 2000, where we have got some on-ground data, is got a higher frequency of events than the preceding 30-odd years. And just a note of caution there, and which I'll go on to in a minute, that our models typically do much better at identifying large events, and so the small events, which can be really critical both for pastoralism and the ecology, are the ones that we have the least confidence in modelling. We can model events which actually don't occur, and then then events can occur which the model just doesn't pick up. And in the Windora Reach, so some examples of this interannual variability. What I've done here is I've just picked, so out of the 49 years of the Curragh River record from sometime in the 30s, I think, through to 1988, this is the 10th lowest flow year, and this is the 24th, so roughly the median here. And I put them on the same Y scale so you can compare them visually. So this is as measured at Curragh River, and then harder to see, but the pinky purple colour there is what went through on the same scale at Napa Mary. And what I want to illustrate here is that even in the bottom half of the flow years, we're getting enormous variability. It's not just looking at the 1974 flood or the 1990 flood and comparing it to all the other floods. Right across the record, we have huge variability. And what that actually means in terms of say, irrigation licences, which currently have no storage and minimum flow requirements before you can start pumping, is that in quite a number of these years you wouldn't be able to take water under those conditions, and then in a number of years you wouldn't actually be able to take your full complement of water either. And then we heard from Ed Fessy yesterday about that variability translates into very poor reliability for the irrigation, which then has that kind of ratcheting effect, is that they say they need more water or perhaps to remove those conditions. If you start to remove that condition about those conditions of no storage and pumping thresholds, that's when you start to take water out of flows, which will probably have much more effect than without those conditions. So we can model these rivers. It's been done, IQQM models being constructed for the Cooper. I've constructed some ones for the Diamantina and parts of the Cooper. So this is from Diamantina Lakes down to Birdsville. And the point I want to make is that the larger events are the easy ones to model. The spatial variability issues are much less. The whole channel is, the whole floodplain's flowing. The rainfall is much more widespread. So we can model these kind of, now this is a 74 flood, and that looks pretty good. You'd show that and everyone would say, oh, great model. But if you looked down here, so this is the observed water coming through Birdsville, and then this is the model, and then you can hardly see it there, but the Birdsville one for this particular event's much less. And so it's these smaller events which we have much lower confidence in modelling, and often the model will over-predict as well. So that's just a note of caution there. How am I going for time? 4 minutes. 4 minutes? Okay, good. And Stuart talked about this yesterday, so I'll just really briefly touch upon it. But it's also in the periods between flow that we need to be, we need to understand these river systems as well. And so particularly that water hole persistence and distribution, which Stuart talked about. This example's again from the Neils. So there's 20 odd water holes in the Neils, which are relatively substantial, going from maybe only a metre and a half deep through to the deepest is about just over, or a bit under, about 4.5 metres here at Algebuckner. These lines here are approximately the annual evaporation loss you'd get from a water hole. So noting that when you hear pan evaporation, that's the evaporation from a pan about that big. That's usually much higher than you'd get from an actual water body, because the air's passing over that pan, it's taking the evaporated water away immediately, whereas over a water body, the removal of the evaporating water is not as quick, and that actually slows down the rate of evaporation, plus you've got shading, etc. But somewhere between, say, 2 to 2.5 metres is probably a feasible measure of evaporative loss each year. So in somewhere like the Neils, after 1 year you've only got a handful of water holes left there. After 2 years of no flow you've got a single water hole. So we do need to identify these really critical refugia and then have some kind of plans in place of how to manage them, because obviously in a dry spell, overfishing, point pollution, all those kind of things become more important. And this is actually from some of Stuart's work on the Cooper, and you saw part of this yesterday, but after a flood, again, the Cooper's something similar. After 2 years of no flow, you've only got a handful of water holes in there. And the deepest water hole that we know of is Culliamurra, just near Inaminka, and that's got a depth of a bit over 25 metres in part of it. Okay, so just to conclude, a bit of a plug for this long-term commitment to measuring data. It can be, and I'm all in favour of targeted measuring, so seeing where the gaps in our understanding are, and particularly putting resources into that. And then just to make this point that our confidence in analysing changes in flow at a particular point in the river system is where we have the least confidence. We can probably have much more confidence in the mean change, the average change, but if it's a particular asset on the floodplain, which is nowhere near a gauging station, that's where we have the lowest confidence in understanding what any changes in the flow will mean for that particular asset. Thank you.